Welcome, fellow explorers, to our deep dive into one of the universe's most enigmatic phenomena, black holes. These cosmic leviathans, shrouded in darkness yet radiating an aura of profound mystery, beckon us to unravel their secrets. From their formation in the fiery death throes of massive stars to their potential role in the very fabric of spacetime, black holes challenge our understanding of the cosmos and ignite our imagination. Join me, Urmila Devi, on this exhilarating odyssey as we venture into the heart of darkness and explore everything you need to know about these cosmic giants. Prepare to have your mind stretched and your perspective shifted as we embark on a journey to the very limits of space, time, and human knowledge. Imagine a place where gravity is so strong, so utterly dominant, that nothing, not even light, can escape its grip. This, my friends, is the defining characteristic of a black hole, a region in spacetime where the very laws of physics seem to break down. But how does such an extreme object even form? The life story of a black hole often begins with the death of a star far more massive than our sun. When such a star exhausts its nuclear fuel, the outward pressure from fusion can no longer counteract the relentless inward pull of gravity. The star's core collapses in on itself, a catastrophic implosion that triggers a supernova explosion, briefly outshining entire galaxies. If the core's mass is sufficiently large, the collapse continues unabated, crushing the stellar remnants into an infinitely small point known as a singularity. Surrounding this singularity is the event horizon, the point of no return. Once you cross this invisible boundary, there's no turning back. The gravitational pull is simply too overwhelming. Think of the event horizon as a cosmic waterfall. As you approach the falls, the current becomes increasingly difficult to escape. But once you're swept over the edge, you're committed to the plunge. Similarly, anything that crosses a black hole's event horizon is destined to meet the singularity at the center. But the singularity is more than just a point in space, it's also a tear in the fabric of space-time itself. Here, our current understanding of physics crumbles. The singularity represents a frontier of knowledge, a cosmic enigma that continues to fascinate and challenge scientists to this day. So, what happens to matter that falls into a black hole? Does it simply vanish from existence? As we'll explore later, the answer is far more complex and mind-boggling than you might imagine. Just as there's a dazzling variety of stars scattered across the cosmos, black holes too come in different sizes and flavors, each with its own unique story to tell. Stellar mass black holes, the most common type, are born from the death throes of massive stars, as we discussed earlier. These cosmic remnants typically pack a mass several times greater than our sun into a region no larger than a city. But if stellar mass black holes are the cosmic middleweights, then supermassive black holes are the undisputed heavyweight champions of the universe. These gravitational behemoths, millions or even billions of times more massive than our sun, reside in the centers of most, if not all, large galaxies, including our own Milky Way. The sheer scale of supermassive black holes boggles the mind. Imagine squeezing the mass of millions of stars into a region smaller than our solar system. How these cosmic titans form and evolve remains one of the most tantalizing mysteries in astrophysics. And then there are the enigmatic primordial black holes, hypothetical objects thought to have formed in the earliest moments after the Big Bang. These ancient black holes could range in size from microscopic specks to billions of times the mass of our sun. If they exist, primordial black holes could hold vital clues to the universe's tumultuous infancy. The diversity of black holes doesn't stop there. Some are actively feeding on surrounding gas and dust, creating dazzling accretion disks that shine brightly across the electromagnetic spectrum. Others lurk quietly in the darkness, their presence betrayed only by their gravitational influence on nearby stars and gas clouds. Understanding the differences between these various types of black holes is crucial to unraveling their role in the evolution of galaxies, the formation of stars, and perhaps even the fate of the universe itself. In the next chapter, we'll explore the ingenious methods astronomers use to detect these invisible cosmic monsters, peering into the darkness to reveal their hidden secrets. Black holes, by their very nature, are masters of disguise, cloaked in a veil of darkness that seems impenetrable. But even these cosmic ninjas can't completely hide from the watchful eyes of astronomers armed with ingenious tools and a thirst for knowledge. One way we detect black holes is by observing their gravitational influence on nearby objects. Just as a rock thrown into a pond creates ripples that spread outward, a black hole's immense gravity warps the fabric of spacetime, causing nearby stars to dance to its tune. By carefully measuring these stellar waltzes, astronomers can infer the presence and mass of an unseen black hole. But gravity isn't the only telltale sign of a black hole's presence. As gas and dust spiral inward towards a black hole, they heat up to millions of degrees, forming a brilliant accretion disk that emits light across the electromagnetic spectrum, from radio waves to X-rays. These luminous beacons act like cosmic lighthouses, guiding astronomers to the black holes lurking in their midst. And then there are gravitational waves, ripples in spacetime itself, generated by some of the most cataclysmic events in the universe, including the collisions of black holes. Like whispers from the abyss, these waves carry information about the black holes that created them, revealing their masses, spins, and even the moment they merged into a single, more massive black hole. The detection of gravitational waves in 2015, a century after Einstein first predicted their existence, marked a new era in astronomy, opening a new window into the universe and providing us with an entirely new way to study black holes and other extreme phenomena. In the next chapter, we'll delve into one of the most groundbreaking achievements in modern astronomy, the first ever image of a black hole, captured by the Event Horizon Telescope. For centuries, black holes lived solely in the realm of theoretical physics, mathematical constructs that challenged our understanding of the universe, but remained frustratingly elusive to observe directly. That all changed in 2019 when the Event Horizon Telescope, a global network of radio telescopes, achieved the seemingly impossible, capturing the first ever image of a black hole. The target was M87*, the supermassive black hole lurking at the heart of the galaxy, Messier 87, some 55 million light-years from Earth. This cosmic titan, with a mass 6.5 billion times greater than our Sun, cast a shadow against the backdrop of its glowing accretion disk, a dark silhouette framed by a fiery ring of light. The image, a testament to human ingenuity and international collaboration, sent shockwaves through the world, capturing the public's imagination and providing stunning confirmation of Einstein's theory of general relativity. It was as if we had finally peered into the abyss and glimpsed the face of a cosmic monster. But the image was more than just a pretty picture. It was a treasure trove of information. By analyzing the size and shape of the shadow, astronomers could precisely measure M87*'s mass and spin, providing crucial insights into the formation and evolution of supermassive black holes. The success of the Event Horizon Telescope has opened up a new era of black hole astronomy. With future observations, we can hope to image other black holes in greater detail, unraveling the mysteries of these cosmic behemoths and their role in the grand tapestry of the universe. Black holes are not just cosmic vacuum cleaners indiscriminately gobbling up everything in their path. They are also cosmic sculptors, warping the fabric of space-time around them, creating strange and wonderful effects that challenge our very understanding of reality. One of the most mind-bending consequences of Einstein's theory of general relativity is that time is not absolute. It flows at different rates depending on the strength of the gravitational field. And nowhere in the universe is gravity stronger than near a black hole. Imagine you could hover just outside the event horizon of a black hole, watching as a friend bravely, or perhaps foolishly, plunges in. From your perspective, time would seem to slow down for your friend, their movements becoming more and more sluggish as they approach the event horizon. From your friend's perspective, however, time would seem to flow normally. They would continue to experience the universe at its usual pace, unaware that you are watching them age at a snail's pace. This time dilation effect, as it's known, is not just a theoretical curiosity, it has real-world implications. For example, GPS satellites, which rely on precise timekeeping, have to account for the effects of time dilation due to Earth's gravity to function accurately. But black holes could potentially do more than just slow down time. They could even provide shortcuts through the fabric of space-time, connecting distant regions of the universe through theoretical tunnels known as wormholes. Imagine a piece of paper representing the fabric of space-time. Now fold the paper in half so that 2 points on opposite sides touch. If you could create a wormhole, it would be like punching a hole through the paper, allowing you to travel between those 2 points instantaneously, bypassing the vast distances that separate them. While wormholes remain highly speculative, their existence is not strictly forbidden by the laws of physics. And if they do exist, black holes, with their immense gravitational pull, could be the key to unlocking these cosmic shortcuts. In the next chapter, we'll embark on a thought experiment, a journey to the edge of the abyss, to explore what would happen if you were to fall into a black hole. Prepare yourselves, fellow explorers, for we are about to embark on a one-way trip to the edge of infinity, a thought experiment to explore the ultimate fate of anyone or anything unfortunate enough to cross a black hole's event horizon. As you approach the black hole, you'd first experience the relentless force of its gravity, but it wouldn't be a uniform pull. Instead, you'd feel a stronger gravitational force on your feet than your head, stretching your body like cosmic taffy in a process aptly named spaghettification. As you descend further, the stretching would become more extreme, eventually ripping apart your very atoms, reducing you to a stream of subatomic particles spiraling towards the singularity. But the journey wouldn't be over yet. The closer you get to the singularity, the weirder things would get. The fabric of spacetime itself would become increasingly distorted, twisting and turning in ways our minds can barely comprehend. Time, as we know it, would cease to have any meaning. Some physicists believe that you might encounter a firewall just inside the event horizon, a wall of intense energy that would incinerate you instantly. Others theorize that you might pass through the singularity and emerge into a new universe, a baby universe born from the ashes of our own. But perhaps the most disturbing possibility is that you might not even realize you've crossed the event horizon. From your perspective, you might continue to fall inward, oblivious to the fact that you've left the known universe behind, trapped forever in the black hole's grip. While we can't say for sure what happens inside a black hole, one thing is clear. It's a place where the laws of physics as we know them break down, a realm of infinite possibilities and unimaginable consequences. For decades, black holes were considered the ultimate cosmic dead ends, inescapable vortices of oblivion from which nothing, not even light, could escape. But in the 1970s, physicist Stephen Hawking turned this notion on its head with a revolutionary discovery. Black holes aren't entirely black. They slowly evaporate over time, releasing energy back into the universe in the form of Hawking radiation. This mind-bending phenomenon arises from the bizarre world of quantum mechanics, the study of the very small. At the quantum level, empty space is not truly empty but teeming with virtual particles, pairs of particles and antiparticles that constantly pop into existence and then annihilate each other. Hawking realized that if a virtual particle pair popped into existence near the event horizon of a black hole, one particle might fall in while the other escapes into space. The escaping particle would carry away a tiny amount of the black hole's energy, causing it to shrink ever so slightly. This process is incredibly slow, especially for large black holes. A black hole the mass of our sun would take an unimaginable amount of time to evaporate completely, longer than the current age of the universe. But as a black hole shrinks, it evaporates faster, releasing energy at an ever-increasing rate. In its final moments, a black hole would release a tremendous burst of energy, a cosmic death rattle that could outshine entire galaxies. While we haven't yet observed Hawking radiation directly, it remains one of the most intriguing predictions of modern physics, linking the worlds of general relativity and quantum mechanics, and offering a glimpse into the potential fate of these enigmatic objects. Thanks for joining us on this journey through the cosmos, exploring the mysteries of black holes, from their formation to their eventual fate. We've peered into the heart of darkness, unraveled the secrets of time and gravity, and glimpsed the potential for new physics beyond our current understanding. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating insights into the universe. The cosmos is vast and full of wonders yet to be discovered. Until next time, keep looking up. Keep